So, previously I talked about 3D printing ceramics to make castings for metals a little bit, among other things. But ceramics I want to go over have a bunch of very useful properties. For example, ceramics can handle some of the highest temperatures of any material. They can be incredibly abrasive and hard, which can be good if you're grinding or etching something. They can act as very good catalysts, especially for things that involve ions and oxygen and gases. Ions are stuff charged particles, usually plus or minus, and they include salts and they can include ions that float around from chemical reactions. They can be used, also ceramics can be used in fuel cells as a catalyst to break down many bad things, toxins and other stuff, and oxidize them. Fuel cells are a way of making energy, kind of similar to batteries, but they don't. This is not fully accurate, but you can think of it kind of like they don't contain both the two materials that react to make electricity, that instead you pump it in, or one of them ones come from the air, like a hydrogen fuel cell. Ceramics can be very strong. They're very brittle though, so not good with flexing and bending. But otherwise, if it's a continuous load, they can be very strong. And there's a bunch of other pretty useful properties of ceramics. Or they can be very good insulators. You can also make ceramics that are like glass to let it light, but light at different frequencies. Not all of them you can see better, and mirrors, and special lenses. So, hopefully that gets you to convince that making ceramic custom parts very useful. Well, I want to talk about 3D printing them so we can get very complex geometries and maybe how we could do that. Well, first of all, is kind of the normal idea. And that normal idea is to have a ceramic embedded, little ceramic nanoparticles, or precursor of it, so what turns into ceramic embedded into original plastic that you 3D print yourself. This has some pretty good pros and cons, but you have to burn off the plastic. And burning off the plastic means that different sections can shrink at different speeds or move around in different ways, which can cause stress, causing cracking in it. Also means you have to waste some materials. Now there might be some ways around this. One is that maybe if we can turn the resins that it's burning off into something useful. Let's say, for example, we could turn it into an oxidizer that turns some metals or other things into the ceramic, because a lot of ceramics are actually metal oxides. We could use it to reduce it if it's something that has too much oxygen, so it can actually react. We could use it to add a lot of carbon, and carbon actually, in Tor, it has a lot of carbon things like carbon nanotubes and stuff have remarkable properties, but they're just not well dispersed usually in ceramics, or they can't handle oxygen very well. But inside the ceramic material, there might not be that much. We could also design these resin stuff to have different properties throughout the different resin to change how the ceramic is formed by changing the amount of pressure, or to add water or something so you have more like a clay that turns the ceramic, or some ceramics that don't. So we could have different resins that changes the curing process, so it can dramatically change the ceramic material. But maybe a slightly better way in the future would be embedding these ceramic nanoparticles that make up it into a metal. Then we turn the metal into a ceramic itself at the site locally with a laser or something that heats it up, and we melt it in other ways in the oxygen atmosphere. Oxygen, this would mean that we get this means that we don't have to worry about as much expanding and stress and stuff, because we locally turn it directly into the ceramic. We don't have to turn all the material at once, and it's less loss of material, because the material turns itself into the ceramic 100% and we waste less material. Also, the thing actually heats up and melts at this higher temperature all at once instead of a slow process. We could also maybe in the future figure out hybrid approaches between these two first ideas I talked about, or sometimes building something and melting it later on with a laser beam and shooting oxygen at it, or an oxygen atmosphere. Oxygen is not the only one. We also can hit with nitrogen in the form of nitride. Either pure nitrogen is hard, but there's ammonia and stuff like that can also make metal nitride, so it's another type of ceramic. You might have heard about, or you can do it with carbonaceous compounds, which is more actually resins could give off. So you can get metal carbides, which is metal plus some carbon. And that one you can add it using something like methane or something like that to the atmosphere. Another idea on top of that is to have a support structure, a stress calculator that is more accurately calculates the stress in the area. Now, as a first approximation of stress and stuff, you can calculate it, just the stress from nearby things pulling or pushing on a little cell. So split up everything into like a grid of cells and calculate how much each of them push or pull on it. That just looks at it very locally. Then you can propagate the stress. So like you first calculate the stress very locally, then you calculate how much the stress farther away from that would impact it, and so on and so on. Then you use that to recalculate how much stuff interacts locally and go back and forth. Now how far away you want to spread is hard to determine, and it also depends on the time scale, because force takes actually time sometimes to move from one place to another one. I will get to maybe a better way of doing that in a second or two. Another kind of way of doing all this stuff is we could also use this to figure out support structures for the ceramic and stuff like that, so it doesn't crack or something as much. And maybe these support structures can be somehow easily taken away. Maybe make it out of a more delicate ceramic itself, so that also expands and stuff. But later on is more machined easily. Maybe it's a granular material, like I said before. Maybe that is just a pure resin thing that really does burn off. Or maybe it's a metal, which metals might be able to support until a higher temperature. A pressurized gas might also keep everything together by pressing on it a little more and squeezing on it as it expands or contracts under heat, and it's giving it a little bit more dynamicism right there. Another idea would be to use something that I'm going to call the ion exchange method, and this is how we make actually stuff like Gorilla Glass, where we take certain ions in glass, usually sodium, and we replace them with potassium. By exchanging them, sodium goes out, potassium goes in, and that can make a glass a lot stronger than it normally was before. So having that idea might be a way of making a material first out of a weaker material, then strengthening it or modifying its surface. And this weaker material might be easier to print because it will probably most likely have a lower melting point, and it will expand probably less. Another way, which I kind of touched on a little bit before in my previous video, was adding little bits of metal into things. And these metals can be heated up using a magnet, and that can give more easily even heating throughout the material as we try to bake or cool it into its shape, or more precise heating control. These metals also might be used to relieve stress or control stress out the material. Yet another idea is to include CNT or graphitic inclusions. Graphitic is a type of carbon nanostructure that's made out of mostly hexagons. Sometimes if it's a buckyball or some other ones with certain turns, so a buckyball is like a ball The most common one is like a soccer ball. This also can be not only hexagons, pentagons. But in the graphitic one, most of them are hexagons, and they're mostly bound to every carbon atom is bound to 3 other carbon atoms. Graphite and stuff is extremely strong, durable, and has many desired properties, but it can't handle the ultra high temperatures when oxygen is around, specifically when oxygen is around, that these other materials can. So it might be good in some parts or not. The last one I want to talk about is developing a better scaling calculator. And this could for understanding support and drying. And this is kind of going back to 4, the stressor calculator here. But instead of, we first look locally. And we look at how locally how much just the local environment affects it. Then we make it a little bigger in this model and see how much stuff farther away really affects it and how much details you have to go in the farther away. Because the farther something away is, the less effect it has and less detailed calculations we have to do. But we do this for many, many different types of structures that could happen with this random arrangements. And then we use that to train a neural network. This neural network then can figure out how to recalculate the stresses in different parts of the structure very well and how it responds by just looking at various scales differently. So it looks at closer with more details and farther away for each point. Just a quick idea right there. Well, thank you very much for listening. Please like and subscribe. It really helps channel out. I'm trying to reach 1,000 subscribers in a year for 1,000 watch hours, but it's really hard. With your help, I think, into it. Again, thank you very much. Goodbye.